Hi, this is Sam, your physics teacher, and here is a short introduction to traveling waves. So here in this graph, we have y as a function of time, so actually not as a function of time. I've plotted y as a function of x, the black line, that is this. So that represents wave. This is the wavelength going from here to here is one wavelength. And then to shift it to the right, you have to subtract d from x. If you add d, it will move it to the left. If you subtract d, and d in this case is velocity times time, you substitute that here, and you can write this as 2 power lambda times x, and then this velocity over lambda ends up being 1 over period. Capital T is the period. So then we can redefine the 2 power lambda as k, the wave number, which by the way is not the same as spring constant. And omega is 2 pi over t, the period, which is angular frequency. By the way, this can also be written as 2 pi times f. F is the frequency. Most people write that in hertz. So this is in radians per second, whereas f is in hertz. Anyway, so this function can also be written using complex notation. In that case, you can write this as exponential of I times kx minus omega t. If you look at the real part of that, that ends up being y equal to a cosine kx minus omega t. So what do we do with this? We take derivatives. So if you take first derivative with respect to time, you get minus I omega times the original function. Take second derivative, you will end up getting minus omega squared times the y. You could do the same with the x variable. So take the first derivative, you get ik times y. Second derivative will give you minus k squared because you're squaring I, and I, you remember, is square root of minus 1, so I squared is minus 1. All right? And so you can relate the second derivative with respect to position to second derivative with respect to time with 1 over v squared factor. V is the velocity of the wave. So it turns out that based on some of those formulas, you can show that this k over w is t over lambda, which is 1 over the velocity, therefore you have velocity squared. Another way to see this is that you have position here, it should be velocity times time. So that's how you can remember it. So this is a wave equation in one dimension. This can be applied to wave on a string, sound waves, waves on water, even electromagnetic waves. So in the case of electromagnetic waves, the y is not actually position, it would be electrical field or magnetic field, and velocity turns out to be the velocity of light. All right, thanks.